Okay, we'll just give it a couple more minutes to give people a chance to join. All right, it's a little after 1:30 here. I guess a little after 2:30 in Vienna. And from what I can see, it seems we have a reasonable set of people in the room and online. So we should get started. Welcome, everybody. This is the IETF Open meeting. My name is Colin Perkins. I'm the IETF chair. As you'll see, I'm remote for this meeting. Thank you to Brian Trammell, who is standing in person, and looks like he is very at home at that desk at the front. So he should perhaps be a little careful. Thank you for standing in, Brian. Yeah, let's get started. So as usual, I'd like to start with a reminder of the intellectual property rules. This is an IETF meeting, and by participating, you agree to follow the IETF's processes and policies around intellectual property, and this means that you, if you're aware of any patents or patent applications relating to the work you're talking about in this meeting, then you need to disclose those. And the details are in the documents linked from the slides and in the note well. In addition, the IETF routinely makes recordings of the online and in-person meetings, and this includes audio, videos, and photographs, and those recordings are published online. If you're participating in person and you're not wearing one of the red do not photograph lanyards, then you consent to appear in such recordings. And if you speak at the microphone, or if you're participating remotely and you turn on your camera and microphone, then you consent to appear in these recordings, and a reminder that this meeting is being recorded and live streamed. Also a reminder that as a participant in the IETF, as an attendee at the IETF meetings, you acknowledge that these written audio and photographic recordings will be made public, and you acknowledge that we will be handling any personal information you provide in accordance with the privacy policy listed. Also, a reminder that as a participant or an attendee in these meetings, whether that's in person or remote, and on the mailing lists as well as in the meetings, that you agree to work respectfully with the other participants, and you agree to follow the code of conduct and the anti-harassment procedures and so on, which are listed on the slide. If you have any questions about this, please do contact the Ombuds team, and again, the contact details are listed there, and they will help you out. And this is the same set of procedures that are in place for the IETF. They also apply for the IETF sessions. And a reminder that since this is this is a hybrid meeting with a mix of in-person and remote participants, if you are attending in person in Vienna, then you need to sign into the session using MeetEcho, using probably the light version of the MeetEcho tool. And you can join that. There's a special icon in the data tracker agenda which allows you to join using that tool. And you need to use MeetEcho to join the microphone queue, since we're managing a uniform microphone queue for both the local and the online participants. And if you're using the on-site version of MeetEcho, keep your audio and video off. For remote participants, please leave your audio and video off unless you're chairing or presenting or asking a question during the session. And again, there's a raise hand button you can use to join the queue if you have questions. If you're having issues with the AV equipment, the URL on the slide allows you to report those or mention MeetEcho in the chat. Okay, so as I say, this is the IETF open meeting, and the goals of the IETF are to focus on some of the longer term research issues relating to the internet. And the IETF works in parallel to the IETF, which does the more shorter term issues relating to engineering and standards making. My usual reminder that the IETF is a research organization. No, it's not a standards development organization. In the IETF, we're here to do research, and we're here to provide a venue where the academic research community, the industry research community, can interact with the engineers and the standard setters in the IETF. But this is primarily a discussion forum, and it's a forum to make connections. And while the IETF, because it's associated with the IETF, can publish informational or experimental experimental documents as RFCs. The primary output of the research groups is expected to be understanding and research results and academic papers primarily, rather than necessarily RFCs. The IETF is structured as a number of research groups. The slide shows the groups which are currently active. Those which are highlighted in dark blue on the slide: the Crypto Forum group, the Path-Aware Networking group, Information-Centric Networking, Measurement and Analysis of Protocols, Network Management, and Human Rights are still to meet. Those which are highlighted in light blue, Quantum Internet Group met in the previous session, the Global Access Group earlier this morning, and the Privacy Enhancements Group yesterday. And the others are not meeting this week, although a number of them have interim meetings closely located. So do please look out for those sessions later in the week, and do join those sessions. Also, for the research groups, I'd like to welcome Sophia Celli, who recently has joined as co-chair of the Human Rights Protocol Considerations Group, which is meeting tomorrow morning, and who's replacing Avery Doria, who stepped down last year. So thank you, Avery, for your service, and welcome, Sophia, and thank you for stepping up, and we look forward to working with you. In addition to the research groups, we also have a number of other activities which we coordinate in the IETF. One of these is the Applied Networking Research Prize, which is something we organize in conjunction with the Internet Society. And the Applied Networking Research Prize is awarded for the best recent results in applied networking. It's awarded for interesting new results that are potentially of future relevance to the standards community. And it's awarded to try and recognize upcoming people that are likely to have an impact on the standards and technologies in the future. And as I say, this is something we organize in conjunction with the Internet Society and with sponsorship from Comcast and NBC Universal. We have two Applied Networking Research Prize talks today. The first talk will be by Sangeeta Abdu-Jyoti for her work on the resilience of the internet infrastructure to solar events, coronal mass ejections, and so on. And the second talk will be by Bruce Spang, who will be talking about A/B testing and some of the fairness problems that arise and the biases that arrive when conducting A/B tests in the presence of network congestion. And we've got two really nice talks coming up, and there are also recordings of these talks and slides available, and links to the papers on the website. So please do stick around for those. We've got two really good talks coming. In addition to the prizes, we also run the Applied Networking Research Workshop, which we organize in conjunction with ACM SIGCOMM. The 2022 edition of that workshop will co-locate with the IETF 114 meeting, which is taking place in July this year, and is expected to be a hybrid meeting with the in-person components in Philadelphia, I believe. The program chairs for that workshop this year are TJ Chung from Virginia Tech and Marwan Fayed from Cloudflare. The call for papers has just gone out recently. The paper submissions are due at the end of April. And the link on the slide again points to the call for papers and more details about that. Please do consider submitting your research results to the Applied Networking Research Workshop. This is a forum for the researchers, vendors, operators, and the standards community to come together and talk about their the latest applied networking research results. We've had a bunch of really good papers in previous years, so please do consider submitting this year. And the final thing I wanted to mention before we go into the talks was that we are pleased to have been running a travel grant program sponsored by Netflix and Comcast. And it's good to get back to this. It's good to have people back in person to at least a limited degree at this meeting. And we're very pleased to have provided a number of travel grants for early career academics and PhD students from underrepresented groups to attend the IETF meetings that are co-locating with the IETF this time. Going forward, we do expect to offer travel grants for the next IETF meeting in July and for the Applied Networking Research Workshop, and keep an eye on the URL on the slide for details of those going up over the next few weeks. And with that, I am done. What we have coming up next is the Applied Networking Research Prize talks. First being Sangeeta, and secondly, in about 30 minutes or so, Bruce will be talking about unbiased experiments in congested networks. All right, so that's all I have. Sangeeta, you should be able to press the Share Preloaded Slides button, and that will let you share the PDF of the slides rather than the Screen Share button.
Oh, okay.
That will work better. Should be a little document icon just next to the hand icon in the top left. Okay, so while that is loading, the first of the awards today goes to Sangeeta Abdujyoti for her work on the resilience of the internet infrastructure to solar superstorms. Sangeeta is an assistant professor at the University of California, Irvine, and an affiliated researcher at VMware Research, and she leads the networking systems and AI lab at UC Irvine. And her research is on internet resilience systems and machine learning. The paper underlying this talk, Solar Superstorms, Planning for an Internet Apocalypse, was first presented at the ACM SIGCOMM conference last year. Sangeeta, over to you. I think you're muted still.
Can you hear me now?
Yes.
Hi everyone, I'm Sangeeta Abdujyoti. I'm an assistant professor at University of California, Irvine, and an affiliated researcher at VMware Research. Today I'll be presenting my recent work on understanding the impact of a cosmic phenomenon that is capable of taking down the internet, which is solar superstorms. What are the impacts of losing internet connectivity? We know that it can affect our professional and social life significantly, especially now during the pandemic. For large businesses, the impact can be devastating. The revenue loss per hour for some of the large companies are estimated to be tens of millions of dollars. And at the scale of countries, it can be hundreds of millions per hour or in billions per day. And it's not just the economic impact. Many of the other critical infrastructure, such as healthcare, depend on internet and will be severely affected. Now, what if we have an internet outage lasting weeks or months and spanning large areas across the globe? One might think that such a global outage is never going to happen because the internet is a resilient distributed system. Um, but unfortunately, this is a worst case scenario that could happen in our lifetime. The next once in a 100-year disaster after this pandemic could be a solar superstorm that is capable of taking down large parts of the internet. And today, network researchers and operators overlook this threat while building our infrastructure. In this talk, I'll present a deeper view of this natural disaster and its impact on various internet infrastructure components. There are two types of solar events that are popularly known as solar storms. They are solar flares and coronal mass ejections. Their impact on global infrastructure varies widely. Solar storms are, solar flares involve large amounts of emitted energy in the form of electromagnetic radiation. So they're essentially flashes of light that reach the Earth in just 8 minutes. Fortunately, they mostly affect only the upper layers of the atmosphere and do not cause any damages to the terrestrial infrastructure. But they do affect satellite communication. Now, coronal mass ejections involve emission of electrically charged solar matter and the accompanying magnetic field into the space. And these CMEs can take anywhere from 13 hours to 5 days to reach the Earth based on their speed. And these CMEs are capable of causing significant damages to terrestrial infrastructure. So CMEs are the focus of this talk, and we'll discuss their impact more closely soon. Both solar flares and CMEs originate near temporary dark spots on the sun caused by concentration of magnetic field flux, which are sunspots. And when the number of sunspots on the surface of the sun increases, there is a higher probability of CMEs occurring. Now, how exactly do these CMEs affect us? The magnetized CMEs are highly directional. And when the Earth is in the direct path of a CME, it interacts with the Earth's magnetic field and induces large electric field on the Earth's surface through electromagnetic induction. And this can cause geomagnetically induced currents to flow through long cables that have ground connections that are located far apart on the Earth's crust. And this could include power transmission lines, oil pipelines, and internet cables that have an electric connection that spans hundreds or thousands of kilometers. Now, next, let's look at some of the characteristics of these induced currents to better understand the risk. So due to the orientation of the Earth's magnetic field, higher latitudes are at a significantly higher risk. And it's for the same reason that auroras are common closer to the poles. And since this impact is caused by interactions with the Earth's magnetic field, the induced currents can affect wide areas and are not just restricted to the portion of the Earth that is facing the sun. GIC is only induced in cables with ground connections and a conductor where the ground connections are located far apart on the Earth's surface. And finally, the orientation of the conductor does not impact the risk associated with GIC. So the north-south or east-west orientation of the cable does not influence the induced current. So that was a quick overview. Now, let's move on to the more important question. When will a large event that affects the Earth happen next? So solar events are extremely hard to predict, just like earthquakes or any other natural disasters. Small scale solar storms happen all the time. What we are more interested in are solar superstorms that can have a significant impact on our lives. So the largest solar events on record occurred in 1859 and 1921, long before the advent of modern technology. The 1859 event is popularly known as the Carrington event, and both these events triggered extensive power outages and caused significant damage to the communication network of that time, which was the telegraph network. And a Carrington scale event missed the Earth by just a week in 2012, very recently. Now, the estimates for probability of occurrence of such extreme space weather events that directly impact the Earth ranges from 1.6% to 12% per decade. But that's not all. The risk is not uniform across the years, because the solar activity goes through cycles. So here we have the variation in the number of sunspots across years from 1700 or so to until recently. And here we can see that the solar activity waxes and wanes in cycles with a period length of approximately 11 years. So during solar maxima, there's an increase in the number of sunspots and hence an increase in the frequency of CMEs and other solar events. And it's not just that, the solar activity also goes through a longer term cycle that is approximately 80 to 100 years. So the peak solar activity varies significantly across this 100-year cycle as well. So this causes the frequency of solar events to vary by a factor of 4 across solar maxima in this 100-year cycle. And if we zoom in, we can see that modern technological advancement coincided with a period of weak solar activity in the past 3 decades. Now we are at the beginning of solar cycle 25, and the sun is expected to become more active in the near future. But due to the absence of extreme activity in the recent past, we have overlooked the impact of these events on the internet infrastructure. So the bottom line here is that large event could happen soon, and the impact is enough that we should prepare our infrastructure for it. Today, we have very limited understanding of how this would affect our internet infrastructure. So how are various internet components affected? So let's start with wired infrastructure. Localized infrastructure such as data centers can be protected from voltage surges caused by CMEs using transient voltage surge suppressors, which are relatively inexpensive. So they are mostly safe. Now, long distance cables constitute the most vulnerable components in the internet infrastructure. So today we know that long distance land and submarine cables carry signals in optical fibers, and this optical fiber itself is immune to induced currents because it carries light and not electric current. But these cables also have repeaters at 50 to 150 kilometer intervals, and which are connected in series and powered by a conductor that runs along the length of the cable. And this conductor is susceptible to damages from induced currents. So today we don't have any good failure models for understanding the failure characteristics of long distance cables. But the expected induced voltages along the length of the cable could be 1 or 2 orders of magnitude higher than what the power system associated with the cable today is capable of handling. And today's cables have not been stress tested under induced voltages that could be caused by a Carrington scale event. So long distance cables are in short vulnerable. Internet routers can be protected from direct voltage surges using voltage suppressors. So most of our localized infrastructure can be protected, so they are safe. Now moving on to wireless infrastructure. Satellites are directly exposed to solar storms. They generally have radiation shielding for protection from high energy electrons. But with very strong storms, it can cause electrons to penetrate deeper into the interior regions of satellite and damage its electronic components. And solar storms can also cause drag on satellites, which can lead to satellites losing their orbit and re-entering the atmosphere and burning up. So very recently, there was news on 40 Starlink satellites that were lost to geomagnetic storm when a small-scale storm hit. But the satellites were just being deployed, and they were at lower altitudes where this risk of drag is much higher, and that's how they were lost. So satellites in general are vulnerable, and this is well known. Cell towers are protected from direct exposure because they are on the ground and protected by the atmosphere. Similarly, personal devices such as laptops and mobile phones are also safe. So to summarize, long distance cables and satellites are the most vulnerable components of the internet. Other components could suffer from power outages, but they are not susceptible to direct damages. Now, analyzing the impact. So to understand the impact on internet infrastructure, I looked at a broad set of data sets comprising of various internet components. So the submarine cable map consists of submarine cables connecting various continents. And then the ITU cable map contains land cable information from across the globe collected from regional entities. Intertube's dataset includes long-haul fiber cables in the US. And then I also looked at publicly available internet exchange point locations, DNS root server locations, and finally router locations with autonomous system mapping from KAIRA. And here we look at the distribution of submarine cable endpoints. So we know that higher latitudes are more vulnerable to induced currents from solar events, particularly latitudes above the 40-degree threshold, so above 40-degree north and below 40-degree south. So we evaluate the distribution of infrastructure components in this region. So here we have the probability density function across various latitudes plotted on the x-axis. So we look at the distribution of population and submarine cable endpoints, and we see that the population is more concentrated on lower latitudes, while submarine cable endpoints are concentrated on higher latitudes, especially between the US and Europe. We see a higher concentration of submarine cable endpoints at more vulnerable regions. Now, next we look at distribution of various internet infrastructure components across the latitudes. So here on the x-axis we have the latitude threshold, and on the y-axis we have concentration of infrastructure component, be it internet routers, IXPs, or DNS root servers, above that threshold. So the most vulnerable region is above the 40-degree threshold, which is denoted by the dotted line here. And here we can see that only about 16% of the population is in this region, but 35 to 45% of the internet infrastructure is in the vulnerable region. And this holds for other components as well. You can see more analysis in the paper. So the key takeaway here is that internet infrastructure components are skewed towards more vulnerable regions. Next, we look at cable length analysis. So here on the x-axis, we have a cable length in kilometers in log scale. So this is a comparison of CDFs of lengths of land cables versus submarine cables. Here the submarine cable dataset is complete. It comprises of almost all existing submarine cables. The LAN cable dataset is not complete, but this was the largest publicly available dataset. So here, shorter cables don't need repeaters. Only cables that are longer than 150 kilometers need repeaters and need that conductor along the length of the cable, which is susceptible to damages. So here we observe that more than 70% of the LAN cables don't need repeaters and hence are not vulnerable. But only about 20% of the submarine cables are shorter than this threshold, which means that nearly 80% of the submarine cables need repeaters and hence are susceptible to damages from induced currents. So in short, submarine cables are more vulnerable than LAN cables. And next, we also look at, we also conducted repeater failure analysis based on latitude-based failure models. So there were several interesting observations. The US faces a higher risk of losing connectivity to Europe during a solar superstorm. So in the East Coast, most cables between the US and Europe are concentrated between the Northeast and the Northeast of the US and the UK, which is most likely done for low latency. And there are no connections from Florida to Southern Europe, which is in the less vulnerable region. But when we look at cables between Brazil and Europe, they're less vulnerable. So it was surprising to find that the cable between Brazil and Southern Europe is shorter than all cables between the US and Europe. And it's also located in the less vulnerable region closer to the equator. In Asia, Singapore has a higher chance of retaining connectivity to neighboring countries, even under severe storms, because cables are much shorter and also located in lower latitudes that are less vulnerable. And here we have locations of public data centers across the globe. Red shows higher density, followed by orange and then blue. So we observe that data centers are concentrated in vulnerable high latitudes. And this observation also holds for hyperscale providers such as Google, Facebook, Microsoft, etc. Now, while data centers won't suffer direct damages, access to these data centers can be affected during a solar event. What about other infrastructure components? So here we have some results on analysis of over DNS and the domain name system and the autonomous systems connectivity. DNS root servers are highly distributed and hence they'll remain reachable even under very high network partitioning. However, location data on top-level domain servers and other authoritative servers was not available, so that analysis has not been done yet. But root servers are highly distributed and reachable. When we analyze autonomous systems, we see that a large fraction of ASS have a presence in vulnerable regions, but the vast majority of ASS have a smaller spread. So next, I discuss some of the open questions and challenges related to this thread. So the paper, my work primarily looked at internet partitioning based on submarine cables alone. Understanding the impact on end-to-end behavior of applications remain an open challenge. This needs to take into account both land and submarine cables, and also better failure models for cable failures. So currently there are some geophysicists working on developing failure models for internet cables. Now the primary analysis only looked at DNS root servers. To understand availability of the infrastructure, we need to analyze the distribution of top-level domain servers and authoritative servers, the extent of caching, etc., to understand the resiliency of the entire system. Another interesting question is, how is AS level connectivity affected by large-scale network partitioning? Next, we need to devise solutions for improving long-term resilience of the infrastructure. For example, this could involve adding new cables in locations that are less vulnerable. Another interesting direction could be the design of interdomain protocols or extension of current ones to improve path diversity in the wide area network during disasters. Another interesting thing with CMEs is that the lead time. So CMEs that originate at on the sun will reach the earth only 13 hours to 5 days later. So this gives us a short interval to prepare for impact. So how can we use this lead time effectively? We can develop plans that allow us to prepare for an impact. So maybe we can cache data across data centers globally in an effective way. How can internet service providers react? Do we need to increase cache time in the DNS system? So there are a lot of interesting questions on how we can use this lead time effectively. And more importantly, we also need to rethink our models of failure analysis. So current best practices on fault tolerance and resilience evaluation rely on failure models that consider a limited number of failures. So we need to test our systems and applications under large-scale failure scenarios. Another interesting direction for research is related to reconnecting a partitioned internet. After a solar superstorm, the internet may be partitioned or due to failures in long distance cables or power outages in certain parts of the globe. Now, can we look at alternative solutions that can provide temporary connectivity after an impact? So examples could be internet collected balloons or high altitude platform stations that are mobile. And ideally, these solutions should rely on renewable power sources such as solar energy to guarantee connectivity even during power outages. So that's another interesting direction of research. Finally, internet and power grids are both designated as uniquely critical because all other critical systems rely on them. They are also interdependent on each other, and both are susceptible to failures from solar superstorms. Hence, we need to study the joint failure characteristics of this complex interdependent system. They also have very different failure characteristics. For example, if we consider the United States, there are three regional power grids: the Western Interconnection, Eastern Interconnection, and Texas Interconnect. Now, if the power grid in the East fails, it will not cause any significant effects or overload on the Western Interconnection. But on the other hand, if all cables connecting to the East Coast fail, there will be significant shifts in BGP paths and potential overload in cables on the West Coast. So internet is more global compared to power grids, and even regional failures can result in significant consequences for the broader internet. So understanding the interdependency is an interesting question. So these are just a few open problems. There are many more. Now to summarize, so space weather, particularly coronal mass ejections from the sun, pose a significant risk to our internet infrastructure. And modern technological advancement coincided with a period of weak solar activity. So the internet infrastructure has not been stress tested under strong solar events. And the complete extent of this threat is yet to be estimated. Internet infrastructure components are skewed towards highly vulnerable regions in the higher latitudes, and this can affect the overall resilience of the system based on preliminary analysis, but a lot more work needs to be done in this context. And finally, we need to work towards better understanding and improving the resilience of the global internet infrastructure. with that, I'll conclude my talk. Thank you, and I'm happy to take questions.
Okay, thank you, Sangeeta. Very interesting talk. Really interesting problem you're looking at here. Wes, do you have a question?
I do. So first off, thank you for the excellent work. I'm a ham radio operator, and we'll pass this on to some friends that are interested in it, because we consider that type of stuff all the time. There's a number of ham radio operators in the IETF. I'm also a root server operator, and so one of the things that I'm interested in is it's worth noting first off that the root instances or DNS instances, maybe that their particular installation does not, pose a problem, but if they become disconnected from the rest of the system, then they will fail to get updates, at which point DNSSEC will stop, validating after, a while as the signatures expire, and regardless of the zone. Did you study islands, or did you find, isolated islands of communication where they would be functionally cut off? I mean, the nice thing about the routing system is that, if a major cable gets taken out, but maybe there's a link to Greenland to, something like that, that you can actually still get traffic through, it'll become congested. But were you able to identify any particular areas that are completely shut off, where, they'd be completely cut off from communication for a while?
Yeah, that's a very important question. So I don't have a complete answer yet. So my initial paper only looked at primary regions of that will be affected, but not the end-to-end disconnection on the complete graph. So currently, I have students that are working on this topic. So I don't have a complete answer yet, but it could be possible that there are very big islands, but not not a lot of tiny islands. It seems like so that based on the preliminary analysis, most of Asia and so the Asia to Europe connection will probably stay, but the US to Europe might be more affected. So complete disconnection, I don't know at this point, but a significant reduction in capacity between the bigger land masses is possible.
Okay, thank you. Anyone else have questions for Sangeeta? There was a little bit of chat about vulnerability of satellites in the chat. I don't know if you saw that.
So the question on the satellite impact on satellites. So Nicholas has pointed out that there are regular solar storms, and apart from Starlink accident with very low Earth orbit satellites are fine. Do you have pointers to justify the assumptions on satellites to be vulnerable? Yeah, so that's a very important question. As I mentioned in the talk, these satellites have protective covering. So typically, when the satellites are deployed, they have shielding that can protect them from solar activity for their lifespan, which is 5 to 10 years or so. So it was only in the past decade or two that the number of satellites grew really exponentially, and we have not had a very large storm since then. The Starlink satellites were affected because after they were installed at a lower altitude than their final orbit, two back-to-back very small scale storms happened. So the solar storms are ranged, the intensity of these storms, they range from G1 to G5, where G1 being the weakest and G5 being the strongest. So the storms that hit the Starlink satellites were G1, which were really weak, but it took down the satellites because the satellites were at a lower altitude than their final destination altitude. Now, if a G5, which is the most intense storm, happens, we don't know the impact, what the impact would be at even the current orbital altitudes. So the radiation shielding can offer some amount of protection, but it's not guaranteed that they'll be completely protected. And not just that, these satellites fall out of orbit very often, and they have mechanisms to they have thrusters that will take them back to orbit. And in order to do that, we need to have connection with the Earth ground stations, which can detect the current altitude and correct the satellite's position. And a solar storm can extend for hours, maybe 10 to 12 hours in the case of very intense storms. So if we lose connectivity to a satellite for such extended periods and they fall out of orbit, it is possible that they could fall. Even though there are thrusters, if we cannot communicate with the satellites, they could get damaged. So before the current International Space Station was installed, US had something called Skylab, which was the previous space station, and that was destroyed in the 1970s during a large solar storm, and they couldn't connect with it to push it back up into the orbit. So with very large storms that extend for hours, it is possible that satellites could be destroyed, but we have not experienced something that large very recently. Does that answer your question, or are there any follow-up questions? Yeah, so there is a question on is the impact focused on high latitude or sun-facing side, or are induced currents the same globally? So when it comes to the direct impact on satellites that are facing the sun are at a much higher risk. But when we look at the induced currents, these are caused by interaction of these magnetic particles with the Earth's magnetic field. So in the case of induced currents, it's not just the sun-facing side, the dark side is also equally vulnerable. But higher latitudes on both the sun-facing side as well as the dark side are equally vulnerable.
Okay, thank you. I had a question. I mean, since this is an IETF and IRTF meeting, is there anything we should be doing differently when we design protocols which would help with this type of, help with resilience to this type of event?
Yeah, so I think we need to rethink resilience at every layer of the stack. So with DNS, as I said, like we know that root servers are very well distributed, but we don't know how the entire hierarchical tree would kind of fare under a solar storm. Do we need to change our caching intervals or change how we manage these DNS records? That's not clear. And then when it comes to protocols, it seems like BGP, which allows only like a single path, that might be too restrictive when the capacity is severely limited. So that's another analysis that we're planning to do, like how would BGP fare in such a scenario. But within an AS, like OSPF or the other intra-AS routing protocols will fare very well because they are decentralized and they can use whatever paths are available in a decentralized fashion. So they seem mostly safe. It's the inter-domain protocol that needs more investigation.
Yeah, okay, that makes sense. I guess there's a whole bunch of coordination issues and management issues with large scale so cloud provider infrastructure networks and so on as well. Yeah, yeah. So some interesting problems. Yeah. Okay. Are there any other questions for Sanjita? Or should we move on to the other talk? DTN over RFC 1149 is clearly the answer. I assume that's avian carriers, right? Okay, I guess there are no more questions. So in that case, thank you Sanjita, excellent talk.
Yeah, and I still back to questions. Thanks, everyone.
All right, next up is Bruce Spang. Is Bruce there? Yes. So the second award today goes to Bruce Spang for his work showing that networking algorithm A/B tests can be biased because of network congestion. Bruce is a fifth-year PhD candidate at Stanford, studying internet networking, video streaming, and theoretical computer science. He's also been a graduate research fellow at Netflix for the past 3 years, working on video algorithms. And in the past, he studied at UMass Amherst and also worked as a software engineer at Fastly. The paper he'll be presenting today is Unbiased Experiments in Congested Networks, which was originally presented at the ACM Internet Measurement Conference last year. And Bruce, you should be able to press the Share Preloaded Slides button.
Great. Let me just share some stuff.
Slides, not the screen. Just
Do you mind
next
if I
to
do
you.
it instead, just for animation and stuff?
It works better if you can do it with the slides, but we can do the screen if
let me give that a go.
Okay, ready when you are.
Great. Well, thanks so much for the introduction. And I guess first off, I wanted to start by saying thank you. So thank you so much for this award. Some of my all-time favorite research papers have received this award, and so I'm really honored that our work is also receiving this award. Our work is about running experiments in congested networks. And this is some joint work with Veronica Hannon, Shravya Kunamala Tuwai Huang from Netflix, and my advisors Nick McEwen and Ramesh Johari from Stanford. So we're talking about networking research, and it's very common in networking research that we come up with some new algorithm, and we want to argue that this new algorithm is better than the existing state of the art. So we've got a pretty typical way that we do this, and normally we come up with some intuition about why the new algorithm is better. Maybe we run some lab experiments that show specific instances where the new algorithm is better. And then finally, we'll go and we'll run a production A/B test. So like a randomized experiment on actual traffic where we try out our new algorithm and see if it actually works well in practice. So this is a pretty standard way to evaluate algorithms. On this slide are a couple of papers from the past decade or so where they rely on an A/B test to argue that their approach is better than the state of the art. And so this is just a subset of the papers that have been published, and also there's lots of unpublished work. So the team that we work with pretty closely at Netflix, they run an A/B test to test basically every single change they make to the production algorithm. And probably over the course of the year, they'll run a couple thousand A/B tests. So what is an A/B test? So in an A/B test, we have a whole bunch of users. And so there's normally a bunch of smiley faces on this slide. So imagine a bunch of smiley faces here. These smiley faces are going to be units. And these units are something like users. They're like video sessions. They're servers. And what we do is we randomly assign traffic to either treatment or control. We wait for a while, we collect some data, and then we look at the outcomes. And so the outcomes, maybe in this case, the treatment algorithm gets better performance than the control algorithm. And so we say, okay, we've run a randomized experiment. We found that the algorithm improves performance. So this is a generalization, this statement that an algorithm improves performance. We're kind of making a statement about what the world would be like if we went and deployed the algorithm based on the results of an A/B test. And typically an A/B test is like a pretty small scale experiment, maybe 1% or less than 1% of global traffic. So this is a fine sort of generalization to make, but it's a generalization that requires some assumptions. And one of the big assumptions is that the outcome of one unit in the test doesn't depend on the other units in the test. So for instance, like what happens to me when treatment is applied to me doesn't matter if treatment is applied to you. So this assumption, this is called interference. And when interference is present, units sort of interfere with other units in the test. And this can bias the outcome of A/B tests. So this is sort of a hot topic in an area called causal inference, which is a field of research where we think about like experiments and how we know what we know is true. And so let me give you a couple examples of this sort of interference. So let's imagine you've got some social network and you've got like a messaging application for this social network, and you want to test some new feature for this messaging application. If you randomize users to treatment and control, and this feature does something that like increases usage for the treatment group, then maybe this user who's in the treatment group goes and messages all their friends who are in the control group, and this will sort of increase usage for both the treatment and control groups, and this will bias the outcome of the test. Another example is from online auctions or markets, and you can think of like eBay or Airbnb here. If you've got users that are randomly assigned to treatment and control, and then they compete against each other in some sort of auction or to buy some sort of product, then if you do something that makes treatment users more likely to win this auction, then it makes control users more likely to lose this auction. And again, you have this interference between treatment and control. There's a lot more examples of interference out there. We've got links to all sorts of papers in the presentation or in the paper. So if we think about it for just a little bit, I mean, this is the IETF, we're talking about networking. It should become pretty clear that interference exists in congested networks. So we've got treatment traffic and control traffic in an A/B test. And this traffic shares the internet, it shares networks in the internet, it shares queues in the networks, routers in the networks, and links in the network. And there are things that we know from, say, congestion control research that the treatment algorithm can do to affect the network. So it can do things like increase or decrease the length of the queues in the network. It can do things like use more or less bandwidth. And if it does this, it'll impact the control algorithm. Like the control algorithm could see the longer queues or could have less bandwidth available to it. So interference clearly exists in congested networks. But the question, it sort of raises two questions. The first question is like, does this matter? So maybe there's a little bit of interference, a little bit of bias, but it doesn't really change the outcome of the test we run at all. Or maybe it does, and maybe it actually would sort of significantly change the decisions even we would make as a result of these tests. So the first question is, does it matter? And if it does matter, then what can we do about it? Is there any way we can avoid this bias? And so in our work, we try and answer both of these questions. Let me start with the first question and tell you about an experiment we ran that shows that A/B tests can be extremely misleading if there's congestion interference present. So this experiment we ran in cooperation with Netflix, and it was an experiment involving bitrate capping. So first, let me tell you about what bitrate capping is. So back at the beginning of COVID-19, everyone started staying home, load on the internet went way up, and governments around the world worked with large video streaming services like Netflix to reduce load on the internet. And the way they did this was by capping bit rates. And overall, this reduced the load that Netflix was sending out by about 25%. So what did this mean technically? So Netflix videos are split up into segments, and each segment you can think about as a couple different seconds of video. Each segment is encoded at a number of different qualities. There's a very high quality one, which looks good, but tends to be pretty large in terms of bytes. Then there's a range of qualities that goes down to some low quality, which is looks less good, but is like much smaller and faster to transfer. So an algorithm goes and it can pick each quality level at each segment, and then at the next segment, it can pick a different quality level. For bitrate capping, what Netflix did was just stop serving the highest quality levels. So they just got rid of those. And so for the same sort of seconds of video, the number of bytes you sent would be lower. And there was a whole bunch of technical details here about how to do this while respecting the various plans that people had paid for and the quality that Netflix had promised. And you can read more about that in the paper if you're interested. But at a very high level, Netflix limited the quality of video, and this reduced the overall traffic. So this is an algorithm that we could test out. And I think it's a pretty natural question to ask is like, okay, so let's say we did run an A/B test for this algorithm. What would an A/B test look like? So let's imagine we've got some congested link. So this link up here on the top left. And we're thinking about a congested link here because the whole point of this bitrate capping thing was to reduce congestion in the first place. So let's imagine we took all the traffic to this link and capped this traffic. So this would reduce the bandwidth usage. And let's say in this case, it will reduce the bandwidth usage by half. And what this means is that now there's some free space available on this link, and the link will become not congested. So there's sort of two treatment effects here of bitrate capping that we're interested in measuring. The first one is how much less bandwidth we're using. And then the second one is how this impacts congestion. So if we were to go and we were to run an A/B test, one possibility is that, so we've got this capped and control traffic, which is sharing a link. The capped traffic could sort of reduce the data that it's sending. The control traffic could be not affected. And there could be some free space available on the link. And in this case, the link would be not congested. So in an A/B test, the results that we would see is that the capped traffic would use less bandwidth than the control traffic. And in fact, here it uses the correct ratio of less bandwidth. So it's using half as much bandwidth as the control traffic. But what we wouldn't see is the impact on congestion, because we would be comparing the capped traffic to the control traffic, and they're using the same link, which is not congested. And so we would see similar metrics for congestion. We would see similar packet loss. We would see similar queuing delay, and so on. A second possibility, if we were to run an A/B test, is that the control algorithm could be running some sort of congestion control algorithm. It could be doing some sort of adaptive bitrate algorithm. And it could notice that there's some free space available on the link, and it could start sending faster or higher quality data and fill up the rest of the link. In this situation, the link could stay congested. And in the result of an A/B test, what we would see is that the capped traffic is using less bandwidth. Sort of directionally, we've got the right direction, but here we will get the wrong ratio. So we'll see that it's using about 1/3 as much bandwidth instead of half as much bandwidth. And then secondly, we're also going to miss this impact on congestion, because both, again, the capped and control traffic are going to be using the same link, which is going to be congested. And so in both of these situations, when we run an A/B test, we're not going to see what happens with congestion. And this is sort of a huge bummer, because the whole point of this algorithm in the first place was to reduce congestion. So now I'd like to tell you about an experiment we ran to measure congestion, to measure the sort of actual effect of bitrate capping. And in order to do that, I need to describe the experiment I ran to you. And in order to do that, let me introduce another way of thinking about the same thing that might make the experiment design a little bit cleaner. So let's imagine we're in this setting back here on the right-hand side, where the control traffic is going to respond to the amount of capped traffic and sort of fill up the rest of the link. So in this setting, we can visualize the behavior as follows. So on the x-axis here is the fraction of capped traffic. On the y-axis is a measurement of per session throughput. And so we've got a bunch of different video sessions here that are sharing one link. And so we can look at a per session throughput for those video sessions. This line here, this is going to be the throughput for the capped sessions. And it doesn't depend on the fraction of traffic which is capped, because there's some sort of upper limit that we send at. And as we increase the fraction of traffic which is capped, there'll be more space available on the link. And so we'll continue sending at this upper level. This line here, this is the throughput for the control algorithm, the algorithm which is not doing bitrate capping. And as more and more traffic is capped, we're going to be back in the setting where the control traffic is going to increase the throughput that it gets. So what we're interested in measuring here is what happens if we were to go and we were to deploy bitrate capping. So that's the difference between when 100% of traffic is capped, which is over here on the right-hand side, when 100% of traffic is running the control algorithm, which is over here on the left-hand side. And the difference between these 2 points, we call the total treatment effect. And this is sort of the quantity that we're interested in measuring. If we were to go run an A/B test, we would not necessarily measure the total treatment effect. Instead, what we would do is we would pick one point on the x-axis where we allocate some fraction of traffic to treatment and control. And then we would compare the 2 points vertically along this line. So we could run this 50% A/B test, and we could look at the difference between capped and control along this line. As you can see from the graph, this is just 1 point, and it might be a biased estimate of the total treatment effect. So here there's some bias, and this can make our estimate of the total treatment incorrect. So sort of the problem here is that we're just looking at 1 point. And if we start looking at multiple points, we can measure capping effects and compare this to the bias of A/B tests. So let's say we did the following. Let's say we could somehow run a 5% A/B test and a 95% A/B test simultaneously. Then we would get 4 points on this graph here. And we could compare this like point on the far left over here when 5% of traffic is capped or 95% of traffic is not capped, to this point over here on the right where 95% of traffic is capped. So this is sort of when we're switching from most traffic not capped to most traffic capped. And we can use this as an approximation of the total treatment effect. And then we can compare that approximation to the results of these two A/B tests, and we could get an estimate of the bias. So this is going to be our goal. One thing that tends to confuse people about this is why here are we picking a 5% and a 95% A/B test instead of, say, a 100% and a 0%? Because the total treatment effect is the difference between over here on the left, 0%, and over here on the right, 100%. The reason we're doing this here is because we're also really interested in measuring the bias of A/B tests. And if we were to pick this allocation of 100% and 0%, we wouldn't have A/B tests to compare it to. So this we thought was a nice compromise between coming up with an approximation of the overall effect of deploying bitrate capping, and then also still having A/B tests that we could compare against. So this is going to be our goal. The real crux of measuring this, though, is going to be to run these two simultaneous experiments. And the problem is, like, as soon as we start running this 5% test, like, it's going to be difficult to run a 95% test because kind of we're allocating the same traffic. So this is where we got extremely lucky. And so Netflix has this content delivery network called OpenConnect. And OpenConnect has a bunch of servers located all around the world that connect with different ISPs. We found this one location that had a pair of very reliably congested peering links to the same ISPs. So there's this ISP, there were these two links, and then there were two routers and sets of servers that were connected to those routers. These two links were very, very similar. So we had the same set of servers connected to the links, the same routers here, the same ISP, the same content was available on all of the servers. And when we looked at historical data, we saw like no significant differences between the two links and most of the metrics that we cared about. So these two links were both congested, both pretty separate from each other. And so what we could do is we could run one A/B test here on these treatment servers and look at how it impacted the congestion on link 1. And then we could run a separate test on the control servers and look how it impacted the congestion on link 2. And so this is what we did. We went on link 1 and we ran a test where 95% of traffic was capped. And on link 2, we ran a test where 5% of traffic was capped. This gave us those two experiments, those 4 points from before, and we could look at and compare the difference between these two things. So now let me tell you about the results of the experiment. So this is a similar graph to what we saw before. On the x-axis is the fraction of traffic which is capped. On the y-axis is a measure of normalized throughput in this experiment. What we saw was in each A/B test, we saw about a 5% decrease in the throughput. So capping decreased throughput by about 5%. But overall, when we compared these two treatments, we saw an improvement of about 12% in throughput. So when we switched most traffic from not capped to capped, throughput went up by about 12%. So the important thing here is that the A/B tests are biased, and they're not just sort of like kind of biased, like even the direction of improvement is wrong. So this is, I think, surprising. And one thing that might make this a little bit clearer is if we look at the behavior of throughput as a time series. So over here on the left is a time series of throughput before the experiment. We've got two links, and as you can see, the two links have pretty much identical throughput over time, over the course of the entire day. During these peak hours, which we shaded here, these are the hours of the evening, load increases. At some point, congestion sets in, and when congestion sets in, throughput decreases pretty significantly, and then it goes back up to normal. So during the experiment, we again have these two links. And this time, the links are split between capped and uncapped traffic. Again, we see during off-peak hours, the links are both pretty similar. But during peak hours, we start to see a difference between these two links. So these top two lines here, this is the first link where 95% of traffic is capped. And the bottom two are the other link where 5% of traffic is capped. Because we're doing capping here, there's sort of less data that we're sending. And in order for the link to be congested, we're going to need higher load. And that higher load will happen later in the day. So when we cap, we delay the onset of congestion for the link which is capped. And we also make congestion end earlier. And so this means that between the two links, the link which is mostly capped is going to have sort of less congestion and higher throughput. But within each link, within the A/B test, the traffic won't see any difference. Yeah, and so there's no difference in throughput between the links, but there is across the links. And this is why the A/B tests are not giving us accurate estimates. So that was for throughput. We also saw this behavior for a couple other metrics that we were interested in. One was round trip time, and the other one was play delay, or sort of how long it takes for the video to start up. In all of these cases, we saw improvements in the total treatment effect, like capping improved these metrics, but the A/B tests sort of didn't even get the direction of improvement wrong. They either reported that the metric would get worse or that the metric was not affected by the treatment. And the A/B test was like extremely confident about this. Like, you compute the 95% confidence intervals, they're very confident that it's 5 to 15% worse in an A/B test, when really it's 25% better. So what this experiment shows is that A/B tests are biased when they're running congested networks. And this to us was pretty concerning because we use A/B tests really heavily to evaluate new algorithms. And if they're not giving us even the right direction in some cases, we're worried about the decisions we might make as a result of these tests. So let me be a little bit more specific about these risks here. Here's a pretty common development process you might use if you're using A/B tests. It's pretty similar to the process that the team we work with pretty closely at Netflix is using. So maybe you'll come up with some idea, you'll implement that idea, you'll run an A/B test for that idea, and you'll get a sense of how the idea performs. And then you'll iterate these steps 1 through 3 until you'll come up with something that works pretty well, and then you'll go and you'll deploy that idea. So the risks here is that when you run an A/B test, you don't get an accurate estimate of what happens when you deploy the idea. And this can have a couple of different consequences. Within the development process, it means you could give up too early on an idea that's good, that would work well in production, just because you don't see it work as well in the A/B test. Or you could continue on with an approach that doesn't work, like when you go and you deploy it, but seems to work well in the A/B test. When you finally deploy the thing, you could deploy something that doesn't work as expected. And in the worst case, this could cause a production impacting issue. Or in probably a more typical case, you might just have to go through this process many more times and improve the algorithm. So those are the risks, but another thing we saw is that we can run experiments that help reduce and remove this bias. So this paired link experiment we described is just one example, and there are other sorts of experiments you can use that are also less impacted by bias. So I'd like to tell you about 2 of these experiments. The first kind of experiment design is called an event study. In an event study, you have some event, and then you compare what happens after the event to what happens before the event. So in this case on the right, we can look at bitrate capping. The event here is going to be sort of switching to 95% bitrate capping. And we're going to do that, say, right here on Friday. So what we would do, we would switch on Friday to 95% capping, and then we would compare after and before. This would give us an estimate of the total treatment effect. And if we switch from, say, 5% capping to 95% capping, we can also compare this to the results of the A/B test and get a sense of whether or not the A/B test was biased. Another good thing about this sort of experiment design is it's pretty common. Folks might already be doing this when they deploy things. So if you go and you deploy a new feature, it's pretty common to look at the metrics before and after the deployment and see how the deployment impacted those metrics. When you do this, you can compare those metrics to the A/B test, and you can start to build up some intuition about whether particular changes are impacted by congestion interference. The big problem with event studies is an issue called seasonality. And this is basically, so you look after some event and compare it to before that event, but there might be other events that happen around the same time, and you're not going to be able to rule out things that were caused by that event. So in this particular experiment, one event here is that we're switching to capping, and another event is that it's suddenly the weekend. And so we're not going to be able to disentangle here the difference between things that are caused by the weekend and things that are caused by capping. One way we can deal with this is with a switchback experiment. This is another sort of experiment design where instead of just switching once, we switch back and forth between treatment and control. So maybe on this day we use capping, on the second day we use no capping, and then we switch back and forth. We compare all the days where we're capping to all the days where we're not capping, and we use this to estimate the total treatment effect. So again, this gives us an estimate of the total treatment effect. And this is going to be more robust to seasonality issues because sort of in order to get the bias here from other events, those events need to line up with most of the switches throughout the experiment. And especially if you randomize the days on which you are using treatment or using control, this can help avoid these issues. The major con here is a carryover effect. And this is when sort of the fact that I'm doing capping towards the end of Thursday is going to change the initial conditions that you see on Friday. And then maybe the whole path of the Friday, say throughput in this case, is going to be different than you would see with control. So this is certainly a risk, but it's sort of a risk that depends on your system. And if you're running experiments, I think you may be pretty familiar with like the carryover, the sort of behavior, the way your system changes over time, and you can design this experiment accordingly. So those are just two sort of experiment designs you can use to avoid some of the impacts of congestion interference. And so I'd like to conclude and say there's a lot more that we can do here. So I think what our work showed is that if you have an A/B test, and this A/B test uses a congested network, this A/B test has the possibility of being biased. There's this pathway for treatment and control to interfere with each other via the use of their shared links. What we don't know is sort of how much this bias matters. We don't know if the bias is going to be a small fraction or a large fraction, especially in experiments that you might be running. Like we know what it is for this one particular experiment, but we don't know what it is for all experiments. And so we would encourage you to go and run some measurements if you are running experiments to see if this kind of interference matters for your experiments. And I think personally, one thing I would really love to see is new papers and new proposals talking about total treatment effects and sort of reporting the results, for instance, when they go and they deploy the algorithm, instead of just the results of a small scale A/B test. And I think mainly what this work highlights is that we have a need for better experiment methodology for networks. So the experiments we've proposed are just a couple of different ways that you could hope to run experiments to measure the total treatment effects. And to be honest, they're experiments we took pretty much without much modification from causal inference work and other experiment literature. I personally think that if we were to sit down and design experiments for networking algorithms, using what we know about networks, we could probably come up with more sophisticated experiments that could give us better results and like more confidence and better estimates of the total treatment effects. And personally, I'm really excited to see the kind of algorithms we could build, the kind of results we could get by using these experiments. So thanks.
Okay, thank you, Bruce. Excellent talk. Does anyone have any questions? Joanna?
I think I'm in. Okay.
Yes, we hear you.
Thank you, Bruce. That was a great talk and good work. And hi, by the way. It's good to see you presenting at the IRTF. I will say that this is very, very illuminating at a minimum. I think it's something that, as you say, everybody should take into account when doing these experiments. And it's great to have the data to back it up and to argue that simple small A/B tests, which I've relied on for a long time, aren't necessarily good enough. But I was going to poke a little bit more at the thing that you just said, which is the dominance of the bias that you see there. In particular, one thing that occurs to me is, I don't know if you've looked into seeing if you made, like, for example, a client sticky for a particular A/B test. As against, I don't know how exactly, I haven't read the paper in detail, but how exactly the choice was made for serving particular type of content. But I imagine that, I guess where I'm coming from is that it depends on where the bottleneck really lies. if the bottleneck is the bottleneck has to be a shared bottleneck in this particular case for the control and the experiment groups. And if, as is commonly the case, the bottleneck is closer to the user and not like at a peering link or some other place, then in that particular case, I imagine that if the user is in a bucket that is either control or treatment, then the user would basically effectively be at the far end of your scale, right? Like where you're seeing that effect. Have you looked into that? Were your experiments sticky to users?
Yeah, so this is a good point that there are things you can do on the allocation side to kind of avoid some of these issues. So the experiments we ran were sticky to users, although it's a little bit tricky because it's like the users that are going over these two different paths. But the sort of overall point you're making is true that like if you sort of can guarantee that the users are not going to share any resources with each other over the whole way, then you're going to be able to avoid this bias because there's no pathway for them to interfere with each other. And if you sort of believe that all of the users are not sharing any of their bottleneck links with each other, then you've sort of avoided some of the possibility for bias. We didn't explore this too much because we found it pretty hard to measure whether or not users were sharing links, and we didn't have a good sense of like how often this was. But I guess, okay, so if you were to allocate users instead of sessions, my gut instinct would be that this is an improvement over just allocating sessions in terms of interference. Another thing you could do is you could allocate networks or particular servers, or sort of try and reduce the probability that there is sort of treatment and control sharing the same link. And if you do this, I think this will reduce the bias that you would see in the experiment.
Yeah, that's very helpful. I was asking this because if you actually did the experiment by trying to, if we try to, it could tell you something about where users end up sharing bottlenecks as well. If you actually tried to do it the way that you were suggesting, any of these ways, those ought to make things better when the bottleneck is closer to the user versus not. And those experiments can actually shed some pretty interesting light on exactly where bottlenecks are on the internet.
Yeah, absolutely.
Thank you again.
Thank you, Jenna. Brian, do you have a question?
Is this microphone on? Can we hear me? That microphone is not on. Let me go to the other microphone. Hi, Brian Dremel, not speaking as sort of, I guess, solar flare backup chair. So there was something that you said earlier that was, I think, kind of fundamental and really interesting that I want to repeat back. If we use what we know about networks to design experiments about networks, we can get a lot smarter about this. And then I was looking at the graph that you had of the switchback experiment, and what that reminded me of more than nothing else was like a diagram of time division multiple access from sort of like a physical layer textbook that I looked at in college, right? So A/B tests are basically code division partition of the space. Switchbacks are time division partition of the space. Like all of the stuff that Jana was talking about were other sort of ways to split the space with different sorts of ways to code it. Are there other bits, like ways to use this multiple access metaphor to find other ways to split the space in order to figure out like how to split this apart? Because like my SRE mind basically wants to say, well, we could basically automate this code partition in a whole bunch of different ways and then, watch which things show up in the power spectrum, which things get amplified out of that. But I'm wondering if there's a more fundamental way that you could split this up in order to be able to, I'm not expecting an answer to that question right now, but if you have one, that'd be great.
Yeah, it's a super interesting question. I don't have an answer offhand, but it's really interesting to think about.
I would be interested in following up with you on an answer to that question because I think there's something like really kind of deep there.
Yeah, I'm happy to chat about it, definitely. I can share a little bit about other experiments that people run, and maybe this will be interesting. So one thing people do in social networks that I think is pretty cool is you would sort of allocate a user and then all of a friend's users to a particular treatment. And you sort of think about this graph structure and how you can allocate based on this graph structure in order to get optimal behavior. And so maybe there's something cool we could do with that for networks.
Yep. Jonathan.
Yes, this is Jonathan Morton. And I think one of the big lessons to take away from this is how important it is to understand the testing methodology in detail when we look at a set of purported results, particularly ones that are used for marketing. So the fine details of the testing methodology can have a big effect, such as exactly how this A/B test may have been done, and whether the potential bias that you've just highlighted has been mitigated in any way.
Yeah, definitely.
Okay, apparently there are AV problems in the room, but hopefully you can still hear us, if not see us.
We can still hear you.
You can still hear us. Okay, good, good. Okay, so I guess I asked the same sort of question I asked to Sangeeta earlier, which is, obviously you're talking to the IETF and the IRTF, and you said there was a need for better experiment methodology. What if anything should we be doing when we're designing protocols, evaluating protocols, to make sure the evaluations and the protocol designs are right? Is there some sort of general guidance we should be providing, or is it read this paper and think about these issues?
I guess overall what I would say is, I think all the stuff we're doing today is good, and we know it's good because we build good systems with the stuff we do today. And I think what this gives us is like another tool to think about how the algorithms work and try to measure like the way these algorithms work. And so I guess kind of when designing new algorithms, like in the IETF, I would think about like the way the experiments we run to validate those algorithms can be biased. And then I would try to think about other ways of running experiments that might reduce that bias.
Yeah, okay, makes sense, makes sense. All right, are there any other questions for the speaker? Okay, I guess not. So in that case, thank you, Bruce.
Thank you.
And again, thank you to both of you, and congratulations on the awards. I do wish we could present these in person, but I'm sure we'll find ways of getting the awards to you. I'm also sure that if people have any further questions, both Sangeeta and Bruce will be happy to answer them and to discuss the work further. So again, congratulations to both of you. We have a few minutes left in the session. If there's any further questions or if anything people want to discuss, I guess we have time for any other business. But other than that, I think we're at the end of the published agenda. So if there's anything else people want to raise, do join the queue. Going once. Okay, in that case, I guess you all get 20 minutes or so back. Thank you, everybody. Congratulations to Bruce, to Sangeeta. Some really nice presentations there. And I will look out for you in the rest of the week and perhaps in Philadelphia. Thank you, everybody.